Okay, suppose we have a function f of x that is of class C infinity in a neighbor of point A, let's say delta neighbor. Then we can define this series, power series, f nth derivative of f divided by n factorial x minus a to the power of n. And if the radius of convergence of this series is positive, so non-zero, and if this is equal to the original function f of x, then we say this function is analytic. And this series, power series, is called Taylor series of this function. And when a happens to be equal to 0, then we, instead of Taylor series, we often call it Maclaurin series. And in this video, we study some of the examples of Taylor series and Maclaurin series. And conversely, suppose we have a power series defined by this, with radius of convergence being r that is positive. So we can define, this is to the power of n, this is defined where x is between a minus r and a plus r. Okay, and let us define a function f of x by this power series. In this case, as we have seen in another video, these coefficients an can be determined as this, nth derivative of f at a divided by n factorial. So after all, this becomes a Taylor series of this function. So when can we represent a function in terms of a Taylor series or Maclaurin series? And here's a lemma that tells us the condition. Okay, let f of x be of class C infinity in a neighbor of, let's just consider Maclaurin series, x equal to 0. And also suppose there is some r that is positive, and suppose this function satisfies the following condition. There exists some positive number m such that for all natural number n, non-negative integers, and for all x in real number, if the absolute value of x is less than r, so this r is this r, then the absolute value of the nth derivative of f is bounded by m. Okay, so suppose this condition is satisfied, then f of x is analytic at x equal to 0, and the radius of convergence of Maclaurin series is at least r. It may be greater than r, but at least it's r. So let's prove this, and let x be a real number from the interval between negative r and r. And then from the Maclaurin expansion, so that's finite Maclaurin expansion, we have f of x equal to the finite sum, okay, from 0 to n minus 1, kth derivative divided by k factorial x to the power of k plus the remainder term, where this Rn, the remainder term, is this. So it's not nth derivative of f at 0, but theta x, and n factorial and x to the power of n, where theta is a real number between 0 and 1. So this is according to Taylor's theorem, if you remember. And this remainder by the given condition here is bounded. So its absolute value is, the absolute value of the remainder is also bounded. N factorial x absolute value. And whatever the value of x is, as long as it's finite, this converges to 0 as n goes to infinity. So that means as n goes to infinity, this right-hand side converges to the Maclaurin series of f of x. So that's this. N factorial x to the power of n. Therefore, f of x is analytic at x equal to 0. And the radius of convergence is at least r. So it's greater than r. And we are done. Okay, let's see an example. And we show that this exponential function, its Maclaurin series is given by this. X to the power of n over n factorial. That is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. And so for that, let f of x be the exponential function. And for any r that is positive, let n be exponential of r. Okay, so if we set this, then for any x that is between negative r and r, we have this nth derivative of x, which is just exponential function itself, is less than this n. So it's bounded. Therefore, f of x is analytic according to the above lemma. Analytic, and the radius of convergence is actually infinity. So this r can be any positive number. So the radius of convergence of this power series is positive infinity. And for any non-negative integers, we have this derivative is just this. So the Maclaurin series is given by this. And related to the exponential function, here is some exercise for you. The Maclaurin expansion of sine x is given by this power series. Negative 1 to the power of n, x to the power of 2n plus 1. So that means this exponent, this power is an odd number. And 2n plus 1 factorial. So that means x minus x cubed over 3 factorial plus x to the power of 5, 5 factorial minus x to the power of 7, 7 factorial, and so on. And also, cosine x is given by this power series. Again, negative 1 to the power of n. In this case, this power is an even number, and 2n factorial, and that is 1 minus x squared and plus x to the power of 4 minus x to the power of 6, and so on. And for both cases, the radius of convergence is also positive infinity. Next, we'd like to study a special class of functions of this form, 1 plus x to the power of alpha, where alpha is any real number. And for that, we define the binomial coefficient, not just for the case where alpha is positive integers, but for the case where alpha is any real numbers. So here's the definition of the binomial coefficient, alpha. So alpha choose n, let's say. So this is defined to be 1 if n is equal to 0. And otherwise, that is alpha times alpha minus 1 times alpha minus 2, and so on, up to alpha minus n plus 1 divided by n factorial. By the way, this last term should be considered as alpha minus n minus 1. Okay? And n is greater than 1. So n should be non-negative integers, but alpha can be any real numbers. So here is an example. So alpha choose 0 is, by definition, it's 1. And alpha choose 1, that is, so alpha times alpha, that is actually n minus 1 is 0, so 1 minus 1 is 0, so that's the end of it, and 1 factorial, and that is alpha. And alpha choose 2, alpha times alpha minus 1 divided by 2 factorial, and that is just this. And alpha choose 3 is alpha minus 1, alpha minus 2, and 3 factorial, and so on. And when this alpha happens to be a positive integer, then this coincides with the ordinary definition of the binomial coefficient. And this can continue forever, but when alpha is a positive number, let's say alpha is n, then alpha choose n is alpha, that is, so n choose n by the definition is n minus 1, n minus 2, and so on, and n minus 1 divided by n factorial. But that is, so this one is just 1 actually, so this is just n factorial divided by n factorial, which is 1. But then what happens when this the lower n becomes n plus 1? In this case, n minus 1, n minus 2, and so on, and n minus 1, then n minus n. So this becomes 0. So this whole thing becomes 0. And when this lower number is greater than n, then this factor always appears. So that means everything after this is always 0. Okay, so that's the case when this alpha happens to be a positive integer. But if it's not a positive integer, then no term becomes 0 in the numerator. So this sequence can continue forever. Next, let's prove this little lemma. That is alpha minus 1 choose n minus 1 plus alpha minus 1 choose n. So if we add these two numbers, we have alpha choose n. So let's prove this. When n is equal to 1, then we have alpha minus 1, n minus 1 is 0, and alpha minus 1, 1. So by definition, we have here 1, and this one is alpha minus 1, so that's alpha, and that is equal to alpha choose 1. So when n is equal to 1, this holds. So if n is greater than 1, then alpha minus 1 choose n minus 1 plus alpha minus 1 choose n. So just apply the definitions, and we have that's alpha minus 1, alpha minus 2, and so on, and alpha minus 1 minus, so n minus 1 minus 1, so that's n minus 2 divided by n minus 1 factorial. And the second term, so that's alpha minus 1, alpha minus 2, and so on. And alpha minus 1 minus n minus 1. So this is n, so it's n minus 1 here. And n factorial here. Okay, so that is alpha minus 1, alpha minus 2, and so on. So alpha minus, that will be n, and that's plus 1. So alpha minus n plus 1, n minus 1 factorial, plus alpha minus 1, alpha minus 2, and so on, and that's alpha minus, let's see, n over n factorial. So let's see. So we have n minus 1 factorial here. And if we multiply both sides, both numerator and denominator by n, we have n factorial. And we have alpha minus 1, alpha minus 2, and all these factors are involved in the second term here. Okay, and so we have alpha minus 1, alpha minus 2, and up to alpha minus n plus 1, and plus this n, plus this alpha minus n over n factorial. But this is just alpha. So let's put this alpha in front here. So that becomes this. And alpha minus n plus 1 over n factorial, but that is alpha choose n. And we are done. Okay, next we consider this power series. N from 0 to infinity, alpha choose n, x to the power of n. If this alpha is a non-negative integer, then this series is actually a polynomial. It's a finite sum of a function of x. And when alpha is not a non-negative integer, then this coefficient is never 0. So this is indeed an infinite series. So let's see when this converges. Let's check the ratio between two consecutive coefficients. So that becomes alpha choose n plus 1 over alpha choose n. Okay, so we use D'Alembert's criteria. And that becomes, so alpha, alpha minus 1, and so on, and alpha, so this is n plus 1, so that's minus n here, n plus 1 factorial, and here alpha, alpha minus 1, here's n, so it's alpha minus n plus 1 over n factorial. So this factorial will factorize, and all these will be cancelled. So after all, we have alpha minus n over n plus 1, which converges to 1 as n goes to infinity. Therefore, the radius of convergence of this power series, radius of convergence is 1. Now, here's the generalized binomial theorem. So it's a binomial theorem. That is 1 plus x to the power of alpha is equal to this power series. Alpha choose n, x to the power of n. And this is a generalization of the ordinary binomial theorem where alpha is non-negative integer. But this applies to any alpha that is real. And this converges, as we have just seen, this converges when x is between -1 and +1. Okay, so let's prove this. First of all, let us define f of x by the right-hand side of this equation. Okay, so f of x is defined by this. And of course, x is between -1 and 1. And so this function is defined on this interval. Okay, so we can apply, since this converges, we can apply the term-wise differentiation. So if we differentiate this function with respect to x, then we have when n is equal to 0, then the derivative becomes 0 actually. So n starts from 1, and n times alpha choose n x to the power of -1. Okay, now let's multiply both sides by x plus 1 plus x. And so that is x1 plus x, and the sum from 1 to infinity. So we put this inside, and wait a minute. Actually, this one is equal to alpha times alpha minus 1 choose n minus 1 x to the power of 1 n minus 1, because let's see, n times alpha choose n is alpha, alpha minus 1, and so on, alpha minus n plus 1 over n factorial times n. So this n is cancelled, and we have n minus 1 factorial here. So put this alpha out, and we have alpha minus 1 up to alpha minus n plus 1, and n minus 1 factorial. And this part can be regarded as alpha minus 1 minus n minus 2. So this is actually alpha minus 1 choose n minus 1. So that's what we have here. Okay, so let's see. Anyway, so we have this, and from 1 to infinity, and alpha is outside, and alpha minus 1, n minus 1, x to the power of n minus 1 plus alpha minus 1, n minus 1, x to the power of n. Now, when n is equal to 1, then this is x to the power of 0, so that's 1, and also this n minus 1 is 0, so that's the coefficient is also 1. So let's put that first term of coming from here outside the sum, and we have, so that becomes 1 plus, then for this summation n starts from 2, so we just shift the index and it starts, so that it starts again from 1, then that becomes n from 1 to infinity, and that becomes, so n minus 1 is replaced with n. Oops. N minus 1 is replaced with n, so that becomes alpha minus 1 and n, and x to the power of n appears in both terms, and we have alpha minus 1, n minus 1, x to the power of n. So by using the lemma we have proved before, we can combine them as alpha choose n, x to the power of n. And this one is, so 1 is just alpha minus 0, x to the power of 0, so we can include this one inside the sum. So that becomes, now sum starts from 0, and alpha choose n, x to the power of n. So this was the function we defined as f. So now we have alpha times f of x. So in summary, 1 plus x times f prime of x is equal to alpha times f of x. And next, let us define g of x by the left-hand side of the target equation, this one. So 1 plus x to the power of alpha, and if we differentiate this, we have alpha 1 plus x to the power of alpha minus 1. So if we multiply both sides by 1 plus x, then we have 1 plus x to the power of alpha, but this is equal to g of x. Now, compare this with this. So we have two differential equations, but they are actually the same differential equations. Now, we can see that f and g are almost the same functions, but maybe a possible difference by some constant factor. So to determine that constant, and we actually want to show that they are exactly the same function. So we define a new function h of x that is the ratio between f of x and g of x, okay, on this interval, okay. On this interval, g of x never becomes 0, so this is fine. So this is the definition of g. So as long as g is greater than -1, then this is never 0. So anyway, so let's differentiate this function, h of x, and so by the quotient rule, we have f prime g minus f and g prime over g squared. Now, using this, let's multiply both numerator and denominator by 1 plus x, then 1 plus x f prime and f of x g prime times 1 plus x and 1 plus x g of x squared. So this is equal to alpha times f, and this is equal to alpha times g. So we have alpha f of x g of x minus alpha f of x g of x. So we have same thing here, and they cancel. So they are equal to 0. So that means h of x is a constant function. So that means f of x is equal to some constant times g of x, right? However, this c, so since it's constant, it's equal to h of 0, and if we put h of 0, then that's f of 0 over g of 0, but in both cases that's 1 over 1, and that's 1. So the constant is 1, so f of x is actually equal to g of x. Therefore, f of x is equal to g of x, and we are done. And this binomial theorem is actually a generalization of the binomial theorem you might have learned in high school. So when alpha is non-negative integer, so natural number, then this becomes a finite sum. So n from 0 to alpha choose n, x to the power of n, right? Because when alpha is an integer, then if n is greater than alpha, then all the binomial coefficient here becomes 0. So all the higher order terms disappear, and we are left with these finite terms. And here's an example. If alpha is -1, then we have this expansion. So 1 over 1 minus x. This is 1 minus x to the power of -1. And this is actually n from 0 to infinity and x to the power of n. So that's 1 plus x squared plus and so on. So to see this, we can apply this theorem, binomial theorem. Wait a minute, this theorem. So alpha is -1 here. So just straightforward application of this formula becomes this. -1, choose n, and instead of x, we have actually negative x here. Okay, so we should consider this as 1 plus negative x. Okay, so that's negative x to the power of n. Okay, and you should show that this is an exercise. -1 choose n is equal to -1 to the power of n. Okay, so if you use this, but you should try to prove this. If you use this, we have and from 0 to infinity, -1 to the power of n. But here we have -1 again. So that's -1 to the power of n, x to the power of n. So this becomes -1 to the power of 2n, which is always positive 1. So we can just ignore this. And we have x to the power of n, which is this. By the way, this is the formula for the geometric progression, right? So here's another way to derive it. Here's a next example, 1 over 1 plus x squared. So by looking at this as 1 plus x squared to the power of negative 1, we have the following series, n from 0 to infinity, and negative 1 to the power of n, x to the power of 2n, okay, because we have x squared here. And by the way, 1 over this function is actually the derivative of arctangent x. So the derivative of arctangent is equal to this series, and this series converges when x is between negative 1 and 1. So we can perform term-wise integration. So therefore, if we integrate both sides, we have arctangent x equal to, so just integrate term-wise, that becomes sum from 0 to infinity and negative 1 to the power of n, and 2n here, so 2n plus 1, x to the power of 2n plus 1, plus constant. And to determine this constant, we put arctangent 0, which is actually 0. So the constant is 0. So we can just get rid of this constant, and we have this Maclaurin series for the arctangent function. Okay, that's all for this video. See you later.